We'll see the complete circuit. So far we have seen basic building block, right? This one. So this will be repeated everywhere. Okay. So the remaining circuits, if you see, I will slowly explain them. Remaining functionality, our cables, everything. First, we try to understand what we are going to do. I'm going to just explain you. Otherwise, I'm going to simulate this multiplication 111 into 111 using the circuit. So while doing that, we understand how this each and every gate is working and each and every circuit is going to do, right? Let's do that. This is actually 7 into 7, 49. I'm assuming that these two are unsigned numbers, then it is 49 actually. Okay, 32 plus 16, 48 plus 1. Now I explained the process how I am doing this one. Initially, I assume that I have a partial product called 0, 0, 0. Then immediately I take the first multiplication, otherwise first row of the multiplication. That means I multiply this 1, 1, 1 with 1. So 1 dot 1, 1, 1, 1. Once you do that, automatically we have to do addition, right? So we will be doing addition. So 0 plus 1, 1, 0 plus 1, 1, 0 plus 1, 1. So this is the partial product 2, let's say. This is partial product 1. This is partial product 2. So this partial product 2, once we get, then again we are going to do multiplication. We take second bit, again you multiply. See 1 dot 1. We know the process, right? Then you add these two. 1, 1, 1. This 1, 1, 1 should be added. Okay. When you do that, you get 1 here, 1 plus 1, 0 here, then 1 comes here. 1 plus 1 plus 1, 1. Then 1 is the carry. 1 plus 1, 0. Then 1 is the carry. 1 will be here. So this is a partial product 3. So remember one thing, if you multiply 1, 1, 1 with 1, 1, you are going to get this answer. Because 7 3 is a 21. This is actually 21. 16 plus 4 plus 1. Once you have this partial product, then you take 1 and multiply this 1 with 1, 1, 1. You get here, see 1, 1, 1. Remember one thing, first time see the positions of 1, 1, 1. Second time 1, 1, 1 here. Every time we have to do left shift, right? So that is one thing you should remember, 1, 1, 1. So 1 here, 0 here, 1 plus 1, that is a process, you understand completely. Now we are going to get the final partial product, which is final product PP4, 1, 1, 0, 0, 0, 1. Okay. So first I will show you where is this 0, 0, 0 computation. That is initially your circuit, which is nothing but your full adder, is going to take 0, 0, 0 as the first input. Full adder will have 3 inputs, right? One is coming from these partial product, second one is carry, third one is AND. Here also carry, this partial product, one of the bit in partial product, and AND gate. Everywhere same thing. Okay. Now, sir, what is this 1, 1, 1? This is nothing but multiplicand. Okay. So this multiplicand can be written like this: A2, A1, A0. I am assuming it is as A0, A1, A2. So I will show here. See, A0, A1, A2. This A0, A1, A2 is multiplied 3 times, right? That means we have to multiply A0, A1, A2 with M0. Let's assume that this 1, 1, 1 as M0. This is M1, this is M2, right? In the first step, we are multiplying A2, A1, A0 with M0, second time with M1, third time with M2, right? So for that, to facilitate that, we will be doing like this. See, A0, first time M0, A0 will be multiplied here. See, M0 dot A0, right? Similarly, just tell me what is the procedure. A2, A1, A0. In the first row, what should happen for first multiplication? M0 should be multiplied with everything. Then you should get M0, A0, M0, A1, M0, A2, right? Sir, where are we getting these products? See here, M0, A0, this one. So this cable is M0. So that is supplied to all the blocks. So here we have M0, but this is A1, right? See. Now, similarly M0, A2. Second time, after some time, in the second row, we will be doing calculation, multiplication like this. What is that? M1, A2, M1, A1, M1, A0, right? Sir, where are we doing that? Please show that. See here. M1, A0, that M1 will be carried here. See, M1 and A1, M1, A1. Now here, see here. This is M1, this is A2, M1, A2. In that way, so we have this multiplications. In the next level, M2 here, M2, what is this one more input? See this one, what is that? This is coming like this, A0. So it is A0, it is A1, A2, right? So M2, A0. Here, this is M2, A1, M2, A2. So in that way, so that is the functionality of AND gate. You understand. Now we'll see the complete story. What is going to happen? focus on the first row first. What is going to happen in the first row we will see. When you give signals like this A0 0, A1 0, A2 0 initially and M0 everything, first this AND gate starts working and everything like all the circuit will start working here, all the circuit. So because of that what is going to happen we'll see. So this 0 0 0 is nothing but this 0 0 0, fine. Second step. So M0 A0, similarly M0 A1, M0 A2, that means multiplication process, this process is done here. So when really if you do that, this is here in this problem it is 1 dot 1 1 1, what you get 1 1 1, right? So that is you are getting here, you see M0, let me take 1, so this is A0 is 1, right? Okay, so 1 dot 1 1, AND gate is giving you 1 as output. Now this AND gate is going to give output 1, let me show here. So 1 1 1, finally we got 1 1 1. Now what is the next step? Once you get 1 1 1, we should add 0 0 0. That's why you see 0 0 0 are added, you see 0 and 1, 0 and 1 are added. Sir, what about this full adder generally takes 3 inputs, right? At this moment it is not relevant, that's why we give 0 input. Another input is just dummy, we give 0. 0 is just for completeness. Full adder has to take 3 inputs, but actually we have to give only 2 inputs. That's why another pin will be connected to 0. 0 plus 1 plus 1. This is done here in this full adder. So what is the result you get? 1, right? So that is output, directly answer, you see. This 0 plus 1, 1 is directly answer, remember, okay? Now, sir, what is this full adder's output? Simple, 1 here. So this, what is the carry of this full adder? 0 plus 1, 1, no carry, right? So 0 plus 1, no carry. Then 0 will be carry here. So now 0 plus 1 plus 0. So this process is going on here. So you get again 1 here, remember it. The sum of this full adder. Next, sir, what is the carry? No carry. So 0 will propagate like this. Now, sir, what happens here? That 0, this 0, and this one is nothing but this one, and one more input, carry, which is 0. These three will be added, so you get a sum called 1. Okay, fine. Sir, any carry? No carry, right? So again same story. 0 plus 1 is 1, so no carry. So carry 0 will be propagated. Now if you see the final answer, so here 0 0 0 plus 1 1 1 is 1 1 1. You can see here 1 and 1 and 1. Perfect. Now next step. In the next step what happens? This 1 will go down. This 1 will come to this block. This 1 comes here. This 1 0 comes here. Okay. Remember it. Now in this step what is going to happen is again this AND gates will develop products M1 A0. Okay. So we know that M1 is 1 in our problem. And A0, A1, A2 for simplicity we took 1, right? So 1, 1, 1. Let us apply multiplication here. M1, A0. You get 1 here. You get 1 here. You get 1 here. Sir, what is this 1, 1, 1 significance? This one. Now see the spatial positions also, right? See here 1, 1, 1 is exactly under this 1, 1. See, this one is important. Let me erase unnecessary things here. Okay. Now, what is important for me is this sum of the full adder 1, 1, 1, correct? So, this 1, 1 is this 1, 1, this 1, 1, 1, right? 1, 1, 1. That 1, 1, 1 should be added to 1, 1, 1. That's why 1, 1, 1 will be added to, see, 1, 1, 1, correct? So, this 1 should not be added to this one. This 1 should not be added to this one. That's why this is the arrangement, right? Now here what is going to happen is this 1 is going to come here, that is what we want. 1 1 will be added. Similarly here this 1 and this 1 will be added like this. This 1 and this 1 will be added. So whatever the carry comes, that will go to the next level. Yes, whatever the carry comes here, that should go to the next level. That is what we built. Okay, we'll just try it out. What happens we will see. So finally in the next level what is going to happen is 1 plus 1. So this block will work first. So 1 plus 1, because it has all the sufficient information. So 1 is coming from here. So this 1 dot 1 is 1, right? 1 plus 1, full adder. 1 plus 1 plus 0. You get 1 here. Okay, fine. Next. So these full adders carry, because 1 plus 1 plus, So here there is a mistake. 1 plus 1 is 0, right? What is the carry? Carry is 1. Then carry comes here. Now let me focus here. 1 is coming from here, this AND gets result 1 and this carry is result is 1. 1 plus 1 plus 1, what is the sum then? 1. This sum is 1. Okay, so what is the carry? 1 here. Okay, now see here, this is 1, this is 1, anything else? See, this one 0. So this full adder's carry is connected here. Okay, then what happens? 0 plus 1 plus 1, 0 is the sum, carry 1. So that carry will be, going like this to the next level. That is what generally happens, right? When you add the things, when you get carry, it should go to the next level, right? That is what happening here. Now just focus on the next partial sum. First partial sum was 1 1 1s, right? Here 1 1 1. Next partial sum should be 1 0 1 0 1. Is that true? We will see. Next partial sum, if you see, so here start. So the next partial sum 1, see here 1 0, I show from here, just mark this one, 1 0 1 0, yeah, 1 1 0 1 0 1. For that 1 0 1 0 1, we have to add again triple 1. So here we are adding triple 1. See 1 1 1, this is triple 1. Okay, so this you can understand slowly that what is going to happen. Now I already explained this one, now I have to explain this box. So what is the result of this box? This full adder is going to give 1, right? This AND is 1, 1 plus 1 0, sum is 0. So carry will propagate like this, remember it. Okay, now come to this box. This box, how you do the calculation? First of all, AND will be done. So we know that the result of AND is already 1, right? So full adder is giving what? 0, right? 0, this 0 plus 1. Now what is the carry? We should know the carry. I have forgotten to tell you. 1 plus 1 0, then carry is 1, right? So here there is a carry. 1 plus 1 is 0, then here carry is 1, right? Now come to this box. Now can I say one thing? This box calculation is depending on this box and this box. This box carry is connected to full adder. This box carry also connected to full adder, correct? That's why we should be careful. Then what happens? 1 plus 1 plus 1. 1 plus 1 plus 1, 1 as a sum. And what is the carry? Carry is 1 again, correct? Remember 1 plus 1 plus 1. So sum is 1, carry is 1. So finally this will be the final carry. Now you see this one. So now answer is 1 1 0 0 0 1. So you check here 1 1 0 1 1 0, then 0, yes 0, then so 1 1 double 0 1 1 double 0, then 0 1, see 0 1. So let me mark them. This is first bit. I can say in the result, let me show result as like this: P0, this is P1 and this is P2, right? This is P3, this is P4, and the final carry is nothing but the P5 bit, this one. Okay, so this is about array multiplier, which is here multiplying two 3-bit numbers. Okay, so 1 2 3 4 5 6 7 8 9, you need 9 blocks. Each block contains one full adder and one AND gate. So these are the details about gates. Now in the exam, what they can ask is, so one time they asked what is the time complexity of multiplication. Okay, so what is the time complexity? We will see. For that, time complexity is nothing but they asked with respect to number of gate delays. Okay, so how many gate delays are there approximately? So they asked in asymptotic notation. That means they did not ask exact answer, but they want to have a rough idea. That means asymptotic idea. Example, when you are multiplying to n-bit numbers, okay, n-bit numbers, then we should get result here, right? I mean, immediately you get result here, and this calculation will be done next level. In the next level, this calculation will be done. After that, this calculation. After that, this calculation. Ultimately, to get the final bit P5, this box should work. But this box is depending on this box and this box, and this box is depending on this sum and this one, right? Because so carry should come from here and sum should come from here, right? So similarly this box is depending on, because this box full adder is connected to this full adder, and one is carry of course 0, but one more thing anything else? No, only these two, right? Carry is of course 0, but it is depending on this one. But this box is depending on, so this full adder is depending on this full adder's carry. So it depends on this one. This box is depending on, so this sum, right? So this full adder's one of the input is connected to this full adder. So this full adder is depending on this full adder because carry is coming from here. So finally I can say that the delay depends on the maximum path length, correct? See, your signal should go like this. So your full adder should give the result that should be taken here. This full adder sum, should come here. Of course, that full adder's carry should come here. Then this full adder should work. So without this full adder, it can't work, right? Because these two are connected. Then signal should come like this, then like this. So easily we can understand that. So the delay is, see, let me count it. 1. I'm just checking how many this box is depending on this box. This box is depending on, of course, this box and this box. Then you see 1, 2, 3, 4, 5, 6. So at least 6 gate delays are there, correct? 6 gate delays are more than that, correct? Otherwise, this entire box has delay x, okay, whatever it is, x delay. This entire box is creating one unit of delay, x delay. Then how many such x delays we have? X generally represents variable, right? For easy understanding, let's assume that this box is having some delay called constant delay c. Now we'll see the delay. So here this box is connected to this box, right? Definitely it is taking the signal from this box, that's the problem. Similarly here, right? And this box is taking signal from this one, this box is taking signal from this one. That means this box calculation cannot be done without this full adder sum, right? That's why, so this box depends here, 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 correct? Yes or no? That's why the maximum delay what I could see is here, you see. Signal has to start here. First of all, this computation of this box should be done. Then we can do this one. Then we can do this one. Then only 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 we can do this one. So finally, this is the longest path in this entire circuit. You see, you take any path, this is the longest path, and your this calculation is depending on that longest path. I will explain very clearly, don't worry. See, 1, 2, 3, 4, 5, 6. This is what the path, and we need this path because we can't escape that path. Why? Try to escape. Sir, I do one thing, sir. I take this path. 1, 2, 3, 4, 5. Correct. After 5 delay, some of the signal is reaching here. What is that signal? This full adder's carry. But we also need this carry, correct? That means we should wait for this box. Fine. So I can say like this, we have to wait for this box for sure now. So, but this box is waiting on this box, that's why we have to definitely wait on this box. Okay. Now what I want to say is this box is waiting on this one, correct? This box is waiting on this one. Sure, of course this box is waiting on this one also, but on this one also. You can take anything. For me same. Now this box is waiting on this one, correct? Because now let me stop and just ask some cross question. Why this box is depending on this one? Because this full adder sum should be taken here, and after that we have to add here, right? So that's why this box depends on this box depends on this box. So that's why maximum delay path is definitely this one. 1, 2, 3, 4, 5, 6. Correct. Now let's imagine you have n by n matrix. Sorry, not n by n matrix. You have n by n multiplication to n bit numbers. Then what I want to tell you is here in every level, see 1, 2, 3, 4, 5, 6. Then how to imagine this for n bit I will tell you. Let me erase this part and I'll explain what is the delay because of n bit multiplication. Okay, see this picture. In this picture, so I am taking 5 bit numbers. Okay, 5 bit number multiplication, then you get this kind of grid, correct? So first signal starts here. 1, first of all signal should go through first block, then second block, right? So when you go to when the signal goes through 2 blocks, we will come here. Now again 1 block, second block. After 2 more blocks, we will come to next level. Try to understand. Initially we have 1, 2, 3, see level 1, level 2, level 3, level 4, level 5. My target is I want to come to level 5 first, because see, this is the ultimate delay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? 12 boxes we have to cross, right? That many delays. Each box has some gate delays, right? So that's why, for easy understanding, we are assuming that one box has some C delay, correct? So how many such C delays we will see? First, we will be in the first level. After two block crossings, then we'll come to second level. After 1, 2. After two block crossings, we'll come to third level. So far we crossed 4 boxes. You can check it out. 1, 2, 3, 4. Then, now one more level, right? To come to one more level, 2 more boxes. One more level, 2 more boxes. So in that way, then we'll reach this point. Then after that, once you are here, 1, 2, 3, 4. 4 boxes we have to cross. Then that 4 represents, 5 minus 1, correct? So now let's generalize it. So here after this 2 plus 2 plus 2 plus 2 plus one more 4, which is nothing but 5 minus 1, right? Then let's extend this to n levels, because when you are multiplying n bit numbers, we will be having n levels, right? 1, 2, 3, 4, 5. We will be in first level. To come to second level, 2. To come to next level, 2. Next level, 2 in that way. See, 1, 2. One level, 1, 2. In that way, how many 2's we are taking? 4. What is significance of 4 again? Because when you are in first level, to come to fifth level, only 4 levels to be crossed. Each time 2 boxes you are crossing, then 2 into that 4 is nothing but n minus 1 levels. Plus, once you come here, 1, 2, 3, 4. Again one more n minus 1, right? So I can say that 3 into n minus 1 boxes we have to cross. Each box has some delay. So that is C. This is rough calculation. Okay, one more or less. I am not exactly calculating, but approximately it is 3 into n minus 1. So I can say that around 3 into n delay, right? 3n. Now the space, if you see, you need huge space. Why? N by n, right? Every row should have n boxes. N into n square. N square boxes you want. Each box has full adder and AND gate, right? So if you are multiplying 32-bit numbers, then 1024 AND gates, 1024 full adders you require, right? Did you remember for addition how much you took? Okay, did you remember? So around some 10, for 32-bit numbers, did you remember? Let's do 4-bit, then you will understand. Let's take ripple carry adder. In the ripple carry adder, see, full adder here, full adder, full adder, full adder, 4 full adders. For 32-bit, maybe 32 full adders, not more than that, correct? But here, n square adders we are taking. So n square blocks or n square boxes we are taking. That is a complexity of space, right? So finally what I want to say is array multiplier is very fast. Okay, slowly you will understand why it is very fast, because it took only 3n box delay, right? 3n box delays. So after some time you realize it will be definitely better thing, because you don't know other algorithms, right? I am going to teach you other algorithms. At that time we will see the calculation again, how much time they are taking. But here there are only 3n delays. It is generally very fast, but at the cost of space. You will be wasting lot of space, okay, lot of circuitry. Remember one thing in computer organization from now onwards, always there will be a trade-off. You can't achieve fasterness without sacrificing your space most of the times, okay? Remember this principle. Without wasting your space, you can't achieve speed in computer organization. Always there will be a trade-off between memory and speed. When you use lot of memory, you can, otherwise memory means here circuits. When you use lot of space, then you are going to achieve fastness, okay? But if you use very less circuits, then sometimes definitely speed will be reduced. Always that will be the trade-off. Just remember it. Just it's observation. It's not a theory. I can't mathematically prove it. But so many times we will be understanding that slowly by different problems. While solving different problems, you understand it. Today you have seen array multiplier, correct? So lot of circuitry, but fast. Now after this one, I am going to teach you sequential multiplier, after that booth multiplier, okay?